Ayesh, have you started the monologue? Yes.
Or mic test. Hello, people. I hope we are audible.
Could someone confirm if we're
Ayesh,
audible or
have you
not?
started the monologue? Yeah, we're audible. Yes.
Or mic test.
The
Hello,
universe,
people.
the
I
miracles it
hope we are
beholds,
audible.
the beauty of it all, and the balance, keeping everything in perfect harmony, has always been a source of wonder for the human mind. In
Could
the early
someone
days of
confirm if we're
humanity,
audible or
our
not?
ancestors would look up in the sky
Yeah,
and
we're audible.
simply wonder about all that there is in the heavens above. And for humankind, so began a tryst with the stars. In the millennia that have passed since, humans have tried to explain what they saw in the night sky using stories, theories, and explanations, greatly influencing the ideas of philosophers and scientists over the ages, and bringing the whole of humanity to what we understand of the universe in the present day. And yet, this is but a drop in the ocean. We just have begun to understand what was, what is, and what could be, what will be. Of course, the wonder itself began billions of years ago, when from nothingness was born all that we see in the universe in a majestic blaze, and the chaos that followed soon after that, in the age of expansion, gave way to order and the formation of the first stars and galaxies in an infinitely complex universe. Over the ages, our own galaxy evolved from the merging of early galaxies and interstellar gases, and our sun and planet were formed from the remnants of these early stars. Thus, the very genesis of humanity can be owed to the stars, deepening our connection to the cosmos and our yearning to better understand the universe. We know where we belong to, where we are from, what are we made of. But to understand where we are going, that is the real question. For everything that has a beginning must also have an end, and so arises the question, will the universe ever end? Upon observing a perfectly balanced cosmos, it is natural to desire its eternal survival. However, in the same manner that stars and planets come to an end, it is possible that the universe too will. Perhaps it may continue to expand until comes a day that all of this might collapse into nothing. The same way that the universe came into being, leading into the next stage of the cosmic catalyst, maybe even a new universe. Or maybe the laws of Newton may apply in a philosophical sense, that the universe will continue to be in a state of expansion and existence through eternity. But whatever the outcome is, we know that until then, we have universe ever end. Upon observing a perfectly balanced cosmos, it is natural to desire its eternal survival. However, in the same manner that stars and planets come to an end, an entire ocean of knowledge to explore. With a universe so vastly unexplored, it is tiring to get tired. And so, join us as we explore the cosmos from the comforts of our homes. That will take our minds to the far reaches of space, to the many wonders that our universe has to offer, and to explore the ancient wisdom immortalized by the cosmos. The universe, the miracles it beholds, the beauty of it all, and the balance, keeping everything in perfect harmony, has always been a source of wonder for the human mind. In the early days of humanity, our ancestors would look up in the sky and simply wonder about all that there is in the heavens above. And for humankind, so began a tryst with the stars. In the millennia that have passed since, humans have tried to explain what they saw in the night sky using stories, theories, and explanations, greatly influencing the ideas of philosophers and scientists over the ages, and bringing the whole of humanity to what we understand of the universe in the present day. The universe, the universe, the miracles it beholds, the beauty of it all, and the balance, keeping everything in perfect harmony, has always been a source of wonder for the human mind. In the early days of humanity, our ancestors would look up in the sky and simply wonder about all that there is in the heavens above. And for humankind, so began a tryst in the universe.
Hello, people. Are we audible? Please say yes in the chat if you're audible.
And we're so sorry for the delay. There's some technical issues, and we'll get started in about a few minutes.
Yes.
So,
We'll get started very soon. Hello and welcome to Celestia's Guide to the Universe. I'm Ishika Praharaj.
and I'm Prateek Upadhyay.
And we will be your hosts this evening.
In today's session, we will take you through the cosmic miracles in the sky above us. We will explore many interesting celestial objects while stringing together a story of how all existence came to be. For those of you who are wondering what this is Space Engine, a realistic, virtual simulation of the universe around us. This virtual universe spreads across billions of light years and contains trillions upon trillions of planetary systems. Keep in mind that everything in this simulation is based on actual scientific observations and data. As we begin our voyage through this universe, everything that you observe is shown exactly as it is thought to be by modern science.
There are a lot of objects in the universe, so you must be confused where to start. If we are going to start somewhere, we may as well start from the beginning. Let's rewind our clocks to what scientists believe is the earliest event in the history of our universe. That is, the origin of the universe, the Big Bang. So, what was the Big Bang? Imagine everything in the universe condensed into one tiny point of matter and energy. This minuscule, dense object not only contained the energy and atoms of everything that will ever exist, it also contained both space and time themselves. This extremely dense point exploded with unimaginable force, creating matter and propelling it outward to make the billions of galaxies of our vast universe.
The universe is so old that the first stars didn't appear until 100 million years after the Big Bang. The universe is so old that the first stars didn't appear until 100 million years after the Big Bang, and nearly a billion years passed before galaxies proliferated across the cosmos. These ancient stars produced and dispersed the first heavy elements, paving the way for the eventual formation of the solar systems like our own. In the words of Carl Sagan himself, we are made of star stuff. This statement throws light on the fact that every fundamental building block, like carbon, nitrogen, and oxygen atoms, that constitutes our body was in fact formed inside previous generation stars. That's amazing, isn't it? So, what better way is there to unravel this universe than to follow the life cycle of a star? So, strap on your seatbelts and get ready to journey through the cosmos to the place where it all began.
Stars, the most widely recognized astronomical objects, represent the most fundamental building blocks of galaxies. But how exactly is a star born? Is there a place where it all happened? Answer is yes. Birthplace of a star is a nebula. A nebula is an enormous cloud of dust and gas occupying the space between stars and acts as the genesis chamber or the nursery for new stars. Turbulence deep within these clouds gives rise to knots with sufficient mass that the gas and dust can begin to collapse under its own gravitational attraction. As the cloud collapses, the material at the center begins to heat up. This is known as a protostar, and it is this hot core at the heart of the collapsing cloud that will one day become a star.
One needs to understand that a protostar isn't stable in nature. It still has large amounts of matter falling inwards, adding onto its mass and helping it grow. And this process isn't quick either. For example, if you look at our own sun and stars of the same mass, the protostar phase would have lasted approximately 50 million years. Once the core temperature reaches 10 million Kelvin, the optimum temperature for efficient hydrogen fusion is attained. It is at this point that the conversion of a protostar into a main sequence star is completed. Though all nebulae are just fundamentally suspensions of dust gas and other interstellar materials, they're pretty diverse objects. They vary in terms of shape, structure, mass, and composition. Some of them contain just enough matter to give rise to a single star, while there are others whose masses are far greater than the mass of our own sun. These nebulae, called diffuse nebulae, give rise to star clusters. The nebula that you see on your screen is a popular example of one such nebula. It is known as the Orion Nebula.
Next up, we have the Red Rectangle Nebula. This nebula is a part of the constellation Serpens, and when viewed through a telescope, looks like a perfect rectangle. And then on the further studies, we found out that it's a bipolar reflection nebula, and thus one of the most symmetrical celestial objects of the universe, as you can see here. It was first imaged in 2007, and its formation is still a mystery.
Intriguing, isn't it? We now journey to the Cat's Eye Nebula. This nebula is part of the constellation Draco and was discovered by Herschel in 1786. Also called the Sunflower or Snail Nebula. The Cat's Eye Nebula is a planetary nebula. Any idea what this means? I'll tell you. A planetary nebula is created when a star blows off its outer layers after it has run out of fuel to burn. These outer layers of gas expand into space, forming a nebula, which is often the shape of a ring or a bubble, as you can see on your screen. Fun fact, our sun will probably form a planetary nebula towards the end of its life.
Last but not least, we have the diffuse nebula with a star cluster, those bright dots you see in the center. What exactly is a diffuse nebula, you may ask? Diffuse nebulae are clouds of material formed from the explosions of the fused stars and leftover hydrogen and helium from the Big Bang. Most nebulae can be described as diffuse nebulae, which means that they are extended and they do not contain any well-defined boundaries. These nebulae are called the birthplace or nurseries of the star.
All of this talk about nebulae makes you wonder about the genesis of our own solar system. Our beloved sun and everything you see today was just an accumulation of dust and gas suspended in space and was called the solar nebula. The solar nebula also went through similar steps while forming our sun. As the mass of the protosun increased, so did its gravity. pulling the surrounding matter towards it. As they fell towards the center, they started to rotate about its axis and formed a disk of matter around the center. Believe it or not, the Sun consumed 99.8% of the total mass of the solar nebula. That's humongous. See, despite having 8 planets and countless objects within the system, they collectively only account for only 0.2% of the total mass. And as the matter of the disk began to cool down, clumps of other matter started to form, which eventually developed into planets, moons, asteroids, and comets. So we can say that all planets in our solar system were made out of leftover material from the sun's birth. This is also the reason why most of our planets in the solar system are found in the same plane.
However, only one of these planets had the perfect conditions for life, and that is our dear Earth, the third planet of the solar system. The rotation of the Earth causes night after day and shows us the incredible night show, the different constellations moving from east to west, each with its own wonderful stories from different legends of various civilizations, and not to forget the beautiful deep sky objects that are present in them. Since time immemorial, humans have been fascinated by the wonders up in the sky. People started mapping the night sky, scaled the time, and prepared calendars based on the celestial bodies and their appearances. The stars and constellations remained the only source of navigation and direction for a long time. The Greek, Babylonian, Egyptian, Indian, Chinese, and many other civilizations all over the world contributed to it in their own ways and gave different hypotheses.
Up until this point, we've spoken about the formation of stars, about how this celestial body came into existence. We now move on to the next phase in its life cycle. You see, these constellations aren't just made of stars, they're also made of nebulae, star systems, and a variety of other deep space objects. As we look at various constellations, we will travel to explore these cosmic entities that are part of them. And in doing so, know more about star systems and what they look like once they get old. Speaking of star systems, a star system or a stellar system comprises of a small number of stars that orbit each other, bound by gravitational attraction. These can be of various types, like binary star systems, which have 2 stars, ternary star systems, which have 3, quaternary, which have 4, and so on. When the system comprises of hundreds or thousands of stars, it's called a star cluster, similar to the one we saw earlier within the diffuse nebula. There are about 88 constellations that have been mapped in the night sky. However, we will be looking into a few interesting ones today. Moving on to the first constellation for today, Ursa Major. This happens to be one of the most easily recognizable constellations, pointing to the Polaris or the pole star in the northern sky. According to Greek legend, Ursa Major was once a beautiful maiden, Callisto, whom the god Zeus had an affair with. In order to protect her and the son Arcus from his jealous wife Hera, Zeus turned them into bears and placed them in the night sky. As Arcus was turned into the small bear, popularly known as the Little Dipper or Ursa Minor, and was being placed into the night sky, he looked at his mother Callisto, now the Big Dipper or Ursa Major. That is why the Little Dipper is curved towards the Big Dipper, so that Arcus can watch over his mother Callisto for all eternity. A cute story, isn't it? In Indian mythology, on the other hand, the 7 central stars of Ursa Major that form the cup shape are referred to as Saptarishis, meaning 7 sages. Ursa Major is visible all year around for observers in the northern hemisphere and can easily be spotted.
Now, let's look at a few interesting deep sky objects present in this constellation. First up, we have Alcor. Alcor is a binary star system, which is a star system consisting of 2 stars orbiting around their common pericenter. These centers, especially when more distant, often appear to the unaided eye as a single point of light, and are then revealed as multiple by other means. Our next destination is located relatively closer to Alcor, that is Mizar, a quaternary star system. Mizar was initially believed to be a single star when first seen from the Earth. It was not until in 1889 that it was reclassified as a binary star. After further studies, we, fi- we find out that it's actually a quadruple star system in which the barycenter of two binary sets are locked into a system, and this system resembles a binary one. Next, from this constellation, we have the pole star or Polaris. This star guided travelers in ancient times and remained one of the most reliable sources to get the north direction. The Indian legend of the Dhruv Tara is the same good old bedtime story we had heard from our grannies back when we were kids. The story of a child named Dhruva who is an absolute devotee of Lord Vishnu and was blessed with the boon of knowledge. On the technical side, Polaris or Alpha Ursa Minoris, which is the North Star, is present at the tail end of the constellation Ursa Minor. This is a triple star system composed of a primary star Polaris AA, which is a yellow supergiant, in orbit with a smaller companion Polaris AB, and this pair is in orbit with Polaris B.
Canis Majoris, the greater dog. This is our next constellation. Canis Majoris, on the contrary, is located in the southern hemisphere. Canis Major is described as a dog with a blazing face, owing to the fact that it holds the brightest star in the night sky, Sirius, in its jaws. This is the reason why Sirius is also called the dog star. The star happens to be the brightest due to its close proximity to our planet, and is just 8.6 light years away from the Earth. However, despite being called a star, Sirius is actually a binary star system, consisting of a main sequence star Sirius A and a faint white dwarf Sirius B. We decided to choose this constellation for a particular reason. You see, it is because it contains another object which is essential for understanding the life of a star, the giants. The main sequence stars, such as our Sun, sustain themselves by using the energy produced as a result of fusing hydrogen into helium. However, there comes a point in every star's life when it runs out of hydrogen. At this point, it starts burning helium. A blue giant is a middle-aged star that has started swelling up. It is running out of hydrogen to burn, but hasn't started burning helium yet. It burns while emitting this bright and beautiful blue light. The reason being, it burns hotter and hotter as it begins to use the remaining hydrogen fuel. Now, after a few million years, the hydrogen reserves are finally depleted. And as a star nears the end of its life, it starts fusing helium nuclei into carbon nuclei. Helium is heavier than hydrogen, and burning it causes the star to expand greatly in size, turning it into a red giant.
Do you know what happens when a star runs out of helium? Well, the answer is pretty easy. It dies. Depending on its size, it dies in a variety of ways. A small to average star will turn into a white dwarf or a nebula. On the other hand, a larger star will experience a stellar explosion, turning itself into the brightest object in the night sky for a few moments. This brings us to the next phase in the life cycle of a star, its death. For stars like our Sun, this occurs as a powerful and luminous stellar explosion called supernova. This transient astronomical event occurs during the last evolutionary stages of a massive star or when a white dwarf is triggered into runaway nuclear fusion in the sky, and it was visible during the day for over 3 weeks. Records of its sighting exist in European, Chinese, Korean, and Arabic sources. Another few interesting facts about this is that it was the second supernova to be observed in a generation. No further supernovae have since been observed with certainty in the Milky Way.
Now, moving on to a stage in the life of a star, the last stage, in fact, we have neutron stars and black holes. A neutron star is a collapsed core of a massive supergiant star. They have a radius in the order of 10 kilometers. Not a lot, isn't it? But the mass of about 1.4 solar masses. They result from the supernovae explosion of a massive star, combined with the gravitational collapse that compresses the core past the normal limit. Neutron stars are super fast spinners, and they are capable of rotating about 716 times per second, which translates to more than 43,000 rotations per minute. Our Sun, on the other hand, is a quiet star. It will eventually turn into a white dwarf when its nuclear fuel dies out. However, this is not the case with many stars, like the one which is 20 times more massive than our Sun. When their fuel supply ends, their gravity overpowers them, and eventually the core collapses into a singularity, a point of infinite density. This brings us to the final frontier of our universe, a black hole. A black hole is a region of space-time where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it. The black hole is so dense that it ends up distorting the very fabric of space and time around it, causing the light to bend and curve. The black hole you see is an ultramassive black hole, which is present at the heart of one of the largest elliptical galaxies found to date. IC 1101 is a supergiant elliptical galaxy at the center of Abell 2029 galaxy cluster and is one of the largest galaxies known till date.
As well quoted by Stephen Hawking, in A Brief History of Time, the universe does not allow perfection. So last but not the least, we have a real treat for you as a grand finale. First up, we have a supergiant orbiting a small black hole. What you see on your screen is GX3394. In this, the black hole sort of feeds off the star in the sense that it absorbs residual gases that the star emits. This system has a very tight orbit, which also causes the elliptical or the egg-like shape of the supergiant or distortion of the star itself. This happens due to the immense gravitational pull. The system does not exist in real life and was only detected due to massive pulsar beams that it emits. Next up, we have Hercules Galaxian Cluster, which is an example of colliding galaxies. This ARP-272 is a pair of interacting galaxies consisting of the two spiral galaxies NGC 6050, which is to the left, and IC 1179, which is to the right. ARP-272 lies around 450 million light-years from the Earth in the constellation of Hercules, and hence the name. This brings us to the end of our space engine, and I hope you guys enjoyed this. But do stay tuned because we have another treat for you.
Next up, Universe Sandbox.
Alright, welcome to the only game where you can end all life on Earth with just one finger, Universe Sandbox. I am Harsh Gujarati.
And I am Anushka Nair. And we will simulate some things which only God can accomplish in the real world. We will collide planets, black holes, and a lot of random stuff. We will find some new ways to destroy life in this universe. Let's get started with a supernova.
As Ashika has briefed you, on what a supernova is. Let's form a supernova by colliding Rigel and Denver. If the stars in one of the binary system collide, or if one of the white dwarf absorbs enough matter from the other star, the white dwarf can become a supernova. Usually, a very dense core is left behind along with an expanding cloud of hot gas, which we called nebula. Supernovae are considered one of the original sources of the elements heavier than iron in the universe. When explosive supernovas happen, stars distribute both stored up and newly created elements throughout space. Even the iron in your blood can be traced back to the supernovae or similar cosmic explosions from long before Sun had formed. Supernovae are thus essential to life. Every 10 seconds, a supernova takes place somewhere in the universe. A supernova of a star more than 10 times the size of our Sun may leave behind the densest object in the universe, black holes.
Speaking of black holes, how about we watch what happens if we place one at the center of a galaxy? A black hole consuming a galaxy is a rare sight, mostly because it's so slow that it is hard to detect the start and the end. The timescale used in this simulation is 0.05 million years passed in a second. And even then, it takes 1.3 million years to fully consume the Milky Way galaxy. That's just how big it is.
If you recall, Pratik and Ishika showed us two currently colliding galaxies. Now, look at something if that's actually going to happen to a galaxy. A collision with Andromeda. When collisions between two galaxies occur, the result is a cosmic firework display. Andromeda is a spiral galaxy of a size similar to the Milky Way and is on a collision course with our galaxy. Spiral galaxies have a broad, thin disk shape with a bulge of stars in their core. Within the disk are winding arms, dark dust lanes, bright star forming regions. This structure is easily disturbed when another galaxy passes near. The neat spiral pattern that the galaxies possess are spun out into wisps and tails, and where dense gas clouds collide, there is glittering dull burst of newborn stars. The Milky Way and Andromeda galaxies each contain a central massive black hole. These black holes will probably converge near the center of the newly formed galaxy. Gravitational interactions may lead to stars being slingshotted into higher radius orbits, and the supermassive black holes to sink towards the galactic. Gases take up the combined black hole to create a luminous pulsar or an active galactic nucleus, releasing as much energy as 100 million supernova explosions.
Next is one of the most beautiful objects we humans have found, pulsar. From Earth, pulsars often look like flickering stars. On and off, on and off. They seem to blink with a regular rhythm. But the light from pulsars does not actually flicker or pulse, and these objects are not actually stars, or at least they aren't living stars. Pulsars belong to the family of neutron stars. These rapidly rotating objects radiate two steady, narrow beams of light in opposite directions. The fastest known pulsars can spin hundreds of times per second and are known as fast pulsars or millisecond pulsars. These magnetized rotating neutron stars are the size of small cities, so ramping them up to such high speeds is no small feat. Here, you're looking at a beautiful simulation of binary pulsars. While Earth has a magnetic field that's just strong enough to exert a gentle tug on a compass needle, pulsars have magnetic fields that can be up to 1 quadrillion times stronger than Earth's. Some pulsars also prove extremely useful because of the precision of their pulses. There are many known pulsars that blink with such precise regularity that they are considered the most accurate natural clocks in the universe. As a result, scientists can watch for changes in a pulsar's blinking that could indicate something happening in the space nearby. Since they move through space while also blinking a regular number of times per second, scientists can use multiple pulsars to make the most accurate distance measurements of cosmic objects in the universe.
The Sun forms an essential anchor for the planets and various bodies in our solar system. Its importance is not just related to how it produces heat and light, but its existence in itself. Say it if were to disappear in an instant and be replaced by another body, a black hole, then what would happen? As we can see, the black hole is slowly swallowing up the contents of our galaxy. And continues to do so. Well, that should teach us about the importance of anchors at the Sun.
The most fun simulations are the ones where many bodies collide and either explode or, in some cases, merge together to form a whole new body. Such can be the case in black hole collisions. In real life, when two or multiple black holes collide, they send out gravitational waves that are ripples of time and space themselves, which can only be detected by highly sensitive instruments. Initially, the black holes are attracted towards each other, and they change their trajectories just a little and then interact with each other before finally colliding. The resultant black hole is even more massive than the colliding ones. There may even be a case where, instead of a direct collision, the smaller black hole revolves around the other and slowly spirals into the larger one. In either case, the new black hole will have a certain velocity, perhaps going on a long journey towards another one of its kind. Now, how about we look at something closer to home? Like other planets, the Earth was formed from the leftover cloud of dust and gas orbiting the young sun. Earth was a very different place, glowing red with rivers and seas of lava. The early solar system was a violent place, and several bodies were created that never made it to full planetary status. One of these could have crashed into Earth not long after the young planet was created. The current scientific hypothesis holds that our moon was born of a calamitous giant impact. Shortly after the planets in our solar system were formed, Earth's impactor, called Theia, collided with Earth around 4.5 billion years ago, throwing vaporized chunks of the young planet's crust into space. After this, the two bodies then recollided. These recollisions left the two bodies with the similar chemical compositions that we see today. This hypothesis is supported by evidence obtained from chemical compositions and observations from the lunar surface, which tell us that the moon's material is derived from the same material as that of our mantle. This lunar origin hypothesis has some difficulties that have yet to be resolved. For example, the giant impact hypothesis implies that the collision would have melted and differentiated the Earth, causing geochemical signatures quite different from those actually observed. The impact should have caused a magma surface to form. Yet, there is no evidence that the Earth had ever had such a magma ocean. We still cannot say for sure how the moon was formed. but it sure is fun to simulate it.
Tidal forces, also known as differential forces, are the secondary effects of gravitational field. These forces stretch other bodies along the line joining the center of mass. These forces are a result of a significant gradient in the gravitational fields. Simply put, the forces experienced on one side of the celestial body exceeds the force experienced by the other side, resulting in generation of stress and heat within the body. There are the main reasons behind tides. Consider this, a case where the moon is very close to the earth. We can notice the effects of these forces. To further view the effects of tidal forces, consider the locked binary Earth system. Just by being close to each other, they start heating up. Consider another binary system of two Earths. Due to the tidal forces, extreme heat is generated within them, leading to super high temperatures and sometimes even explosion of one body over a period of time. Research is going on about how it can be more efficiently utilized. We all have had our share of destructive tendencies sometime or another, and well, we almost always blame the world. So let's try to bombard our beloved blue marble everyday object. One possible thing is that usually life always escapes complete extinction, even if it is by a meager percentage. Not this time though.
Now, we have some random objects here with which we will bombard Earth at different speeds. You guys get to suggest to us in the comment section which object we should bombard the Earth with. How about we start with a banana? A banana at a speed of around 3.4 kilometers per second. Now pigeons. At a speed of around 3000 kilometers per second.
Anushka, we've got Jupiter, we've got Titan,
All
we've
right.
got a golf ball at light speed, we have a banana. Some people are suggesting
Let's
bananas
do
again.
an asteroid, I guess. How about an asteroid? Wow. Looks like we've evaporated all the water on Earth. What else can we do? Cone, yes. How about a cone? Made a small impact in Africa right there. Now for a cube. At a much higher speed. That left an impact. Pluto definitely left an impact on Earth. Someone wants another Earth on Earth. Let's see how that works at 10 times the speed of light. Very slow asteroid. Forward one. Around 300 kilometers per second. Alright, let's look for more suggestions. Sun. People want to crash the sun into Earth. Let's see if we can make that happen. Goodness, our planet has been scorched.
Finally, using a Death Star laser, we will destroy this planet the Star Wars style. Unlimited power! Now that we have destroyed the Earth, we will answer your questions about the session and more importantly about the club in the chat. So you can put your questions in the chat box.
Regarding the session or the club, you can put them in the chat and we'll try our best to answer them.
I guess everything is delayed, so we'll have to wait. We'll have to wait for some time. How will we get inducted into the club? That's a great question, Janil. You fill the form, and then we'll contact you back with an interview, and that's simple. Actually, that's simple. What do we do at the club? Satvik Gupta. We do a
We
lot
throw
of
planets at each other.
Is it?
Okay, I see a question which asks, what is the induction schedule? You can go ahead, and the inductions will probably be somewhere in February.
INSAT, I think someone asked about INSAT. Hello.
Yeah, you're
Yeah,
audible.
Yeah,
they wanted to know what INSAT is about. So
Okay, cool. Can I get who exactly asked it? Can you give me a name? I'm sorry, I'm
yeah.
just I just came in this meet right now.
it's Swapnil, if I'm not wrong.
Okay,
Swapnil
Swapnil.
Torwar. I'm
Okay,
sorry
cool,
if
cool.
we
Swapnil,
mispronounced the name.
I'm Kaustubh. I'm the lead of INSAT. So, INSAT is basically a CubeSat project which is going to be deployed at a lower orbit of around 400 or 420 kilometers. So our main goal is to have a uh, basically a telescope assembly on the CubeSat and monitor a specific star for exoplanet transits. So for that, we'll need a very good telescope, a very good image sensor, and a very good pointing assembly. Basically, the CubeSat should point very well towards a particular object. So there are a lot of challenges which we face, are there in the design itself. It's a big design goal. It's a big goal for implementing such design. It's a pretty big project. It's a very multifaceted project. You need to understand how to code. You need to understand how electronics work. You need to understand how to design and manufacture printed circuit boards. How electronic circuits work. How do you model a CubeSat? How do you orbit a CubeSat? Like the list goes on and on, basically. So there is a lot you guys can work on, and there is a lot to learn as well. So uh, if you guys want to know more about this project or any Celestia projects in general, you can either talk to me or any of the POs currently. Any questions? If
I
you
guess
guys have any question, just ping me up. Uh, I'm a little busy right now. Cool. Thank you.
Vishnu Rajagopal asks, what kind of activities are done? Well, Vishnu, we do a lot of activities. We have a lectures team which brings in guest lecturers, and they do guest lectures at our university. We have a podcast team as well, which releases podcasts whenever they get certain guests. We have a YouTube vertical as well, which is currently working on a YouTube team. We have an observations team, which conducts observation nights in on campus. We're also hoping that we'll be called back to campus soon, so that we guys can have observation nights with you as well. Observation nights are one of the most fun things that I have personally experienced on campus. And we also have a lot of projects which are going on. If you get inducted into the club, and if you manage to stick, you can suggest a project. You can lead your own projects. We do a lot of projects related to STEM. You can check out our website. We have details of previous projects there as well. Aryan Thakur asks, can you please elaborate on pulsars? Pulsars are basically fast spinning neutron stars. They have a huge magnetic field, and they emit a lot of magnetic fields as well as radiation, and they rotate at also very high speeds. So, considering that you're a stationary point on Earth, what you see especially is that a star is just pulsing data. So, and since the rotation of that is so precise, we use it for measuring stuff in space. You can check out further videos on YouTube, or you can search about it and research about it more. Any more questions, guys? Please. Do you make satellites at campus? Pratham asks. Yes. Yes, we do.
Wait, who was that?
Pratham. There's a guy in the chat. I guess Cube can
We
answer.
satellites, uh, satellites on campus, per se. At the moment, we've built prototypes, but we've not tested them. I mean, not to the altitudes that we would like to. So again, they are a work in progress phase and stuff. So, but yeah, once these guys come back to campus, they'll be building their satellites and stuff. But yeah, it's a very long process, like Kaustubh said. You tend to go through multiple virtual prototypes before fixing on one, and then you make one out of cheap materials that you get, and then you figure out the flaws in it, and then you start, building the actual model. It takes generally 2 3 physical prototypes and several virtual prototypes before you actually build the final product and launch it or do whatever with it. But yeah, that's the basic idea. I mean, if I can hijack this thing for 5 minutes, I'm hijacking it for 5 minutes, okay? So
Go ahead.
basically, today these guys talk to you about what do you say? About astrophysics. I mean, they pretty much showed you what it's like to be in space using space engine and all the different sorts of celestial bodies, objects, messier objects in space, black holes, pulsars. And I just wanted to stress on one fact that at Celestia we are not really restricted by this. We do much more crazy stuff. We've made projects and we've had projects. There was this project called astrobiology where the goal was to generate electricity using try to identify the kind of bacteria by figuring out what sort of voltage output they give in soil. So whether it's a bacteria, whether it's a cyanobacteria or if it's some other sort of a bacteria, we do. And if you guys also, we also try following deep tech. If you know how the COVID pandemic unfurled, and you might know how what do you say, the how actually COVID this thing virus was, the protein behind it was unfurled, the point where the virus attacks, and the whole deep mind AI behind it and stuff. We have we do research. I mean, not research exactly, but we have discussion sessions on that. We try to replicate some of it. You'll get to know seniors who do a lot of stuff in that field over due course of this time. And from Celestia, I'm not sure if these guys mentioned it, but Celestia is the club that gave birth to RT and Kratos in sort of a way, I would say. Mm. So yeah, join Celestia. I mean, you don't have to know physics and astrophysics per se to join Celestia. I joined Celestia as a very dumb student who knew nothing in physics, and Celestia didn't help me anything in physics, but they helped me figure out my passion for robots and self-driving cars and stuff like that. So do, I mean, come to the interviews with a jolly mind and relaxed thing. It's not your job interview or something like that. It's a club. And so yeah, fill the form. And I guess my hijacking is over. There's no pre-induction test. Don't think of it as a test. Think of it as an interaction. We interact with you to see if you're best fit for our club. That's about it. There's nothing else. There's no pre-induction test today. No, that's the thing. Kartikeya Gupta, you don't need to complete projects and coding. There's no prerequisite for it. You come to the club and then seniors list out projects. And once you go to a project, the senior ideally tells you what to study, and if you have doubts, he teaches you stuff on that. He or she teaches you stuff on that, and then you go forth from that. You learn while doing projects, pretty much like what Tanmay said. Uh, There's just one rule at Celestia: you don't trash talk Star Wars. You're fine as long as you don't do that. Or else there are a couple of people who go haywire and nuclear like Hrithwik. So yeah, come join the club, enjoy your time here, and yeah, pretty much that's it. I've stopped hijacking the meet. Whoever wants to speak next, go speak.
Okay, thanks again, HV. Where can we get the form? I think Anushka has already hammed it. Okay. Okay, I guess that's all for tonight. Thanks, everybody. You've been a wonderful audience. And thanks for joining in. It really means a lot to us as a club. And I hope this event has sparked your interest. We do have one more pre-induction event on the 29th. It's a pop sci event. You're supposed to, we're going to be telling you the faults in physics in certain movies. We're going to be talking about the science between after, sorry, I jumbled. We're going to be talking about science behind certain scenes in movies, and we're going to be talking about a lot of physics. So please, if you guys are all interested in the club, please attend our second pre-induction event as well. You'll be getting the details soon via WhatsApp. And if you have not joined our uh, WhatsApp pre-induction group, please do so. Please fill up the forms. Thank you for being a great audience. And good night. Good evening. Akshat, Sayesh, has the stream ended?